Let's talk about how you would drive a brushed DC motor. So we already talked about the construction and theory behind a brushed DC motor. Also, a DC motor means that we're operating at a constant voltage, not an AC voltage. AC motors also exist. They work a fair amount differently than this. So the circuit that we're about to make for driving the DC motor would not work at all for an AC motor. So don't try this with a motor that plugs directly into the wall. Okay, so our motor electrically usually just draws a circle with an M. That's our motor. And we know that when we apply a voltage to the motor, it spins at a certain velocity, angular velocity, based on our motor equation. So V equals kT omega. And the torque that the motor produces is related to torque equals kT times I. So if we put a voltage on this motor, we should make it spin and generate some torque. So we want to do that controllably with our microcontroller. So why not just take the motor, hook it up to ground, and connect this to a pin on our microcontroller. And we can even do that with one of our PWM pins, because the PWM at a high frequency would average out through the motor, and then we can essentially get any voltage between 0 and the maximum pin voltage, say for the PIC32, 3.3 volts. So we could go from 0 to 3.3 volts on this motor, and if it's a low enough power motor with low enough friction, we can make it spin. So why doesn't this work? Well, most pins on our microcontroller, first of all, would be like 0 or 3.3 volts, not particularly high. Also, they're going to be 0 to, most of them, like 5 milliamps of current. So the motor typically takes on the order of hundreds of milliamps, and the stall current could easily be in the amps. So we're not particularly limited by the voltage, although that's a low voltage, but the pins just can't output enough current to make the motor spin. So we can hook up LEDs directly to our pins, and we can make them moderately bright enough to see them, but the power that comes out of the pin cannot make the motor move. So that means we need an amplifier to turn on the motor. So instead we'll have our pin go to our amplifier, and the amplifier will direct the current to ground, and we'll start with some voltage that will go to the motor, and the motor will connect to the amplifier. That amplifier is typically a transistor or a switch. So if you want to think of it as an NPN transistor, it'd be like that. Or we could just think of it as some kind of voltage-controlled switch, like a MOSFET. Depending on what electronics class you've learned, you can think of it as a relay. But basically, the pin is telling the switch to open and close. That connects the motor to ground, so that the motor, one side is power, and the other side would be ground through the amp. And that's what would direct current to go through the motor. This would be called a low side connection. You could also think of an amplifier that goes in between the voltage source and the motor would go to ground. That kind of switch is typically requires a higher input voltage to turn on and off, which our pin usually has a low voltage compared to the supply voltage. So typically we use these low side switches, NPN transistors or N-channel MOSFETs, not P. Okay, so now the pin turns on the amplifier. That connects to ground. We've got our raw voltage source directly connected to the motor. So as long as it can provide enough current to drive the motor without the voltage dipping, we can get our motor to produce torque and to spin. The downside to that, though, is let's talk about what is inside of our motor. So we talk about the motor as just this motor block. Well, its model is that it's inside of it a resistor and an inductor. So really, when we circle that M, we're saying inside of it is some kind of resistance and some kind of inductor. And it's a little complicated because it's really a resistor and an inductor, right, wound together. But what do we know about these two things? Well, if we apply a voltage across this device, if it were just a resistor, it would produce heat with Ohm's law. And the inductor does not like to change current instantaneously. So the voltage for an inductor, that's L di dt. So when you apply a voltage across this motor, if the current is not changing, essentially all the voltage is across the resistor. If the current is changing a lot, then all of the voltage is across the inductor. If all the voltage is across the inductor, there'll be no voltage across the resistor. There'll be no current. If you have no current, you have no torque. So the motor must be going at its maximum speed. So this is a kind of complicated system, right? We're applying a voltage to the motor. It's drawing whatever current it needs to spin the load that it's attached to. This is a second order system. So that's what makes motors so complicated to talk about. But back to this situation where we have a single pin turning on a switch to make the motor move. The problem comes down to this inductor. Let's say that the motor has come up to some speed. So there's a lot of current going through the motor, maybe because it's not necessarily at the maximum no load speed, because then there's no current. Let's say it's just sitting somewhere on the motor speed curve. So it has some current through it. Then you want the motor to turn off, so the pin turns off, the amp turns off, the switch opens, disconnecting the motor from ground. Well, when you take a wire that has current going through it and you chop the wire in half, the current has to go to zero, right? Because the conductor is not continuous, no more current can flow. What does the inductor say? Well, the voltage across the inductor is di dt. So if we go from some current to zero current, di dt is going to be big. The voltage on the motor, across the motor, is going to spike because of this equation for the voltage across the inductor. What does that mean? That means that this point here, which was ground, when the pin turns the amp off, that used to be 0 volts. That voltage is going to spike. And when it spikes really big, it could get really high. It could go up into hundreds of thousands of volts for a very short period of time before it dissipates. And when it does that, it could arc across the amplifier. So the switch, which is just two pieces of metal, has air in between it. If it's kind of like a relay, there's a breakdown voltage due to the air gap there. So if the voltage across those two wires gets large enough, you'll get an arc that goes across them and spark. Same thing for any transistor inside of the metal housing. It can only take so much of a big voltage before it arcs. And a lot of times that kind of arc will then push a lot of current through the transistor, and the transistor has a maximum current rating, so the transistor will burn out. So if you're driving a particularly noisy or high power motor with a single transistor or amplifier like this, and you're turning on and off, which of course you're going to do, you will probably be burning out a lot of amplifiers. The way we fix that is by adding a diode. We need to give the voltage a way to dissipate and send the current not through the amplifier but somewhere else so that it doesn't burn out our amplifier. So instead, we'll have our pin goes to this voltage controlled switch, which is going to ground. One side is attached to our motor to our power supply. We'll put a diode in parallel to the motor, facing up towards the voltage source. So if the diode faced down, then the current would just go around the motor, right, and then the ground. So this is a backwards facing diode. This is called a flyback diode. So the switch is closed. It's been closed for a long time. We've got some current going through the motor. We open the switch to turn off the motor to make it stop spinning. This voltage will spike. How big can it spike? Well, if this is a regular diode, it would have a 0.6 volt voltage diode. So when this voltage gets to V plus 0.6, suddenly this diode turns on. It can conduct. The current that was going through the motor will continuously go back through the diode into the power supply. So that's, sometimes you think of that as the regeneration effect. If you have a Prius and you hit the brakes, and the brakes move a rotor and push energy back into your battery, try to recharge the battery. So that's what's going on here. Instead of opening the switch, letting this voltage spike very large, creating a spark, burning out our switch, the diode turns on and goes back into the voltage supply. And typically use a special diode, not a normal diode. So the forward voltage is probably 0.1 or 0.2. It would be some kind of shocky diode, and a very high power diode, because if there was an amp going through this motor, at the instant the switch opens, an amp has to keep going through that motor. This can't change instantaneously, so for a very short period of time you get 1 amp going back that way into the power supply. So you better hope that your power supply can accept current back in at that high rate. Sometimes special kinds of like lithium polymer batteries, they don't like that. So you should have a big capacitor in parallel with your battery to absorb that voltage back in. Okay, so flyback diodes, very, very common when you're driving brushed DC motors. and basically any coil. So also solenoids and anything like that. Okay, so this would make the motor move in one direction. If we can apply a positive voltage here and a ground here, we get current in this direction, the motor spins in one direction. If you want to spin the motor the other way though, we need to get the current to go this way. So how do you get the current to go the other way through the motor if one end is attached to ground? Well, the voltage that you apply would have to be negative, right? Because that's the only way you can get current to go from the ground side of the motor to another voltage would be if this voltage can be either positive or negative and the other side of the motor is grounded. That's annoying. That means you need two batteries, one that's positive voltage and one that's a negative voltage. And you need two switches, one that goes to positive, one goes to negative. Typically, we don't have that kind of thing. So let's imagine another configuration for our switches around our motor so that we can drive the motor in both directions using just one power supply. This is called an H-bridge. And you'll see why in a second. So we'll put our motor in the middle, and we'll have our single voltage supply and our connection to ground. If the single voltage supply can go through a switch and this switch, and we close both of these switches, well then current could go that way through the motor and make it spin. Let's say that, positive current makes it go clockwise or something. Okay, then if we open those two switches and instead we close this switch and this switch, then we can get current to go that way through the motor. So close that switch, and it follows that path to ground. So now by closing, let's call this 1, 2, 3, and 4. If you were to close 1 and 4, you would get the motor to go that way. If you close 2 and 3, you get the motor to go that way. You could also close 3 and 4. That would be called braking. So if both sides of the motor are shorted, the current that goes through the motor when you spin it would go back through the motor. I suppose you could also do this with pins 1 and 2, but typically it's done with the grounded ones. That would make the motor, the current that goes through the motor, dissipate through the motor's own resistance. And so the current would dissipate faster than as if all the switches were just open. Something you don't want to do is you don't want to close 1 and 3 or 2 and 4. What happens if you close 1 and 3? Well, the current just goes straight to ground and you get fire, shorting your battery. So the device that has these switches needs to make sure that it kind of opens the switches before it closes other switches. So it needs to get the command that says, I want to close these two, or I want to close these two, and give enough delay between switching of on and off to make sure the switches are all the way open before it tries to close any other, or you'll get a short and you'll get a lot of heat through those switches and you'll burn out your H-bridge. Also, each of these switches can see the sparks due to the inductance of the motor. So there must be flyback diodes, one for each switch. Okay, so for flyback diodes, let's think about which flyback diode is protecting which switch. So up here, we saw that this diode was not in parallel to the switch that it was protecting. It was across the motor. So slightly different configuration here. So let's pretend that we've closed switches 1 and 4, and the current is going this way through our motor. Okay, now we're going to open switch 1 and we're going to open switch 4. That's the bad condition because the motor had a certain amount of current going through it. At the moment the switch is open, it must still have that same amount of current going through it because the current in the motor can't change instantaneously. But when we've opened those two switches, for those for that current to continue going in that direction, that must mean that this voltage is current must be coming either from this direction to go that way, or it must be coming from this direction. So which one is it going to have? Well, the current can't be coming in this direction because this diode's in the wrong way, but it can come up from this direction because this diode would let it flow. If this is 0 volts, what does that make this voltage? That makes this the negative forward voltage of the diode. I'll just put that as 0.6 because that's what we typically think of as a diode, but these are probably special diodes, Schottky diodes, so that might be like 0.1 or 0.2. So at the moment this switch opens, this diode starts conducting because this voltage, which can change instantaneously, jumped from V down to like negative 0.6. Okay, that means that this voltage, what's going on over here, the current is coming this way. It can't go through that diode. It's facing the wrong direction. It must be going up through that diode. So when this switched open, this diode starts to conduct. This voltage, for the current to be flowing through that diode to that voltage, this voltage must be higher than this voltage by the forward voltage. So this is like V plus 0.6, or whatever the forward voltage of the diode is. So we used to be applying V across the motor, V and ground. The moment we open the switches, now we've got negative 0.6 and V plus 0.6. So we've got V plus 1.2 volts across the motor at the moment we open the switches. That, of course, very quickly dies away because we're no longer supplying that voltage. This is the back EMF generated voltage plus the inductor-induced voltage of the motor. So that's pretty crazy. This is also a great question in an interview whenever you do a mechatronics job using an H-bridge. What's the maximum voltage you ever see across the motor? Great question. Just talk about how H-bridges work and what the flyback diodes do. Okay, how do you build an H-bridge? You can do this with transistors. We can use N-channel transistors down here and P-channel transistors up here if we have the appropriate amplifiers to drive those, because to drive a P channel, to turn it off, you need to apply this voltage to the gate. Complicated. You could use N channel, but same problem, you need a bigger voltage to apply to the gate. Typically though, you don't try to build this from discrete chips. You buy an H-bridge chip. In our class, in the textbook, we will be using the DRV 8835. DRV is from a specific manufacturer. 8835 is one of their chips that contains two full bridges. So one of these double sets of gates, that's usually called a half bridge. Each half bridge could drive a motor, one pin of a motor high or low. So if you have a solenoid, you can drive the motor, you can close the solenoid, or you can open the solenoid. It goes in one direction. So one DRV 8855 can drive 4 coils. If you want to drive one coil in 2 directions, one brushed DC motor, one H-bridge. So this can drive 2 brushed DC motors. A stepper motor, bipolar stepper motor, has 2 coils. So one DRV 8835 could drive 1 stepper motor. Or you could take the 2 full bridges and put them in parallel and drive 1 brushed DC motor with effectively half the resistance or twice the maximum current that the DRV 885 can provide. The only downside to this chip, so just like any other device, you think about what's its maximum voltage and what's its maximum current. The downside to this particular chip is that it's 0 to 11 volts. Excuse me. That's too bad. For a 6-volt battery, that's great, but for a 12-volt battery, you'll burn out your chip. So just pay attention when you're buying an H-bridge. What is its maximum voltage? You probably want to go over the battery voltage by a certain amount, but that's another video. This also has a maximum current. It's around 1 amp. But if you put the 2 outputs in parallel, you would get 1.5 or maybe 2 amps. There's a continuous current and there's a maximum like small peak current. Usually there's a peak current of like, say, 2 amps on this chip. So you could briefly go up to 2 amps if you stall, but you don't want to sit there forever because the chip will overheat. So these kinds of chips have a VCC voltage. That's the logic voltage, so it's typically something like 3.3 volts. And then a VM, a motor voltage. That's what this would be. So that's like your battery voltage. They usually have 2 sets of grounds. Remember that whenever you have 2 power supplies, they need to have common ground. So the 3.3 volts has a ground on the NU32. The battery, when you think of a battery as like it's an 11-volt battery, and it's got a ground, its ground has to be attached to the H-bridge ground. Both of the grounds need to be attached to each other. That's called common ground. If you have many power supplies going on and all the chips are talking to each other, common ground means all the grounds are connected. And you don't want to connect them in a loop. They should all connect to each other in one central point that's called star ground. Then we've got inputs in 1 and in 2 that goes to out 1 and out 2. And there's a mode pin that selects how do these inputs connect to the outputs. When the mode pin is low, in 1 directly controls out 1 and in 2 connects to out 2. What's unique about the DRV8835 though is that if you attach the mode pin high, the ins do not directly connect to the outs anymore. Instead, one can be controlled to PWM and the other can be controlled to just a regular I/O pin, just one that goes high or low. It doesn't do PWM. And they call them enable and phase, and I always forget which is which, so check the datasheet. I don't want to do all the work for you here. But that means that O1 goes to the motor and O2 goes back to the H-bridge, the two motor leads. One pin from the PIC controls the speed of the motor, and the other controls the direction. When the mode pin is low, both of the pins have to be capable of doing PWM to get the motor to be able to change direction and speed. So this is kind of nice when you have an H-bridge that has this type of mode pin, that you can have only one pin using PWM to control the speed of the motor and the other control the direction. If you want the motor to turn off, just set your duty cycle to 0, and then it doesn't matter what the direction pin does. When the motor is on, so when the PWM is high versus low, this kind of H-bridge usually goes between brake and drive. There are also H-bridges out there that would allow you to go between brake and coast. So the more complicated the H-bridge, the more inputs there would be. You can look for that kind of thing if you ever don't want to just be drive and brake.